Can I start?
Okay, so it's a pleasure to have Luigi Guerrini from Parma, and he will be telling us about Latitude Wilson loop in ABJM and dual line operators. Please.
Okay, first of all, thank you for the invitation. So today I'm going to talk about the Latitude Wilson loop in ABJM. Then ABJM is an n=6 supersymmetric Chern-Simons matter theory with this quiver structure. And the observable I'm considering are supersymmetric Wilson loops. They are specified by the representation, the curve gamma supporting the loop, but also by this matrix M, which measures the coupling of the this matter scalar C and C bar to the loop. The standard example is the great circle, which lives on the equator of a sphere embedded in the three-dimensional space. It is 1/6 BPS, and it is characterized by this constant matrix. The loops preserve an SU1,1/1 superconformal algebra on the circle. The simplest but non-trivial deformation we can consider is the latitude, which is 1/12 BPS. It can live on an arbitrary circle of this same sphere. And the coupling is characterized by a deformation parameter nu, and it's also depend on tau, which is the coordinate along this circle. As I said, the loop preserves a small algebra, which is this SU1/1, which is Poincaré, because nu breaks the conformal invariance. This operator is interestingly related to the Bremsstrahlung function, which is the two-point function of the displacement operator of the 1/6 BPS circular Wilson loop. So the relation is given in this formula. And this Bremsstrahlung is not only a crucial parameter for the defect CFT on the circular Wilson loop, but it also provides us with a bridge with integrability, because this quantity in principle can be computed with localization, but also with integrability. And so this is a computation that can be in principle used to fix the important parameter H on the integrability side. Anyway, today I'm going to discuss only the localization part. So for nu=1, we recovered the great circle. In this case, there's a well-defined localization scheme provided by Kapustin, Willett, and Jakob. So the results amounts to insert this exponential in the ABJM matrix model. Here we see the classical contribution and the one loop determinants, which are for the vector, this sinh squared, and for the matter, this cosh. For the latitude, there's a similar prescription, but there are some differences. So there is always this exponential insertion, but now depends on nu. The matrix model has this form, but the functional determinants are slightly different. They are deformed by this square root of nu. This matrix model reproduces correctly the partition function, but it gives a different prediction for the two different Wilson loops. So maybe someone has noticed that the functional determinant are those of the squared sphere. And to understand this, we need to look at the square of the localizing supercharge. And we found that it appears the same Killing vector of the squared sphere, the stand of the circular Wilson loop of the squared sphere. We find also a gauge transformation and an R-symmetry transformation. So how can we argue that the one I showed before is the correct matrix model? The first step is to assume that an off-shell closure for this localizing supercharge is possible, and it's possible using these cohomological multiplets introduced by Cullen. The important fact is that this gauge transformation coincides with the connection of the Latitude Wilson loop. This is important because it allows us to argue that the BPS locus is characterized by two constant matrices, one for any gauge groups, as in the standard localization. But since we have this different vector, we have a different functional determinant, which is the one of the square-shaped sphere. It's more subtle to reproduce the matter determinant because we have to interpret this R-symmetry transformation, which is an actual R-symmetry from the n equals 6 point of view, as a mass deformation for these cohomological multiplets. In this way, the parameters recast in a nice way, and we can reproduce the hyperbolic cosine. Now one can ask how, if we can compare our result with the known localization scheme. So the first observation is that our supercharge can be actually embedded into an n equal 4 subalgebra. In this way, we understand that for nu equals 1, we recover the usual n equal 2 structure of Kapustin-Willett-Yakov, but also for nu equals 0, we find that this, our supercharge coincides with the one used by Pufo and collaborators to study the topological quantum mechanics defined for n equal 4 theory. Moreover, since ABJM at k equals 1 is infrared dual to an n equal 4 super-Yang-Mills theory with an adjoint hyper and a fundamental hyper, we can ask which are the dual loop operator for our latitude. To answer this question, I need to introduce all the defect, the disordered version of the Wilson loop, which is the vortex loop. So since they are disordered operator, I need to specify the singularity of the gauge field through an holonomy around the curve. And also in this case, I can impose this BPS condition. And Asser and Gomis show that these operators are mirror symmetric to the BPS Wilson loops. They also provided a nice defect description of the loops in terms of one-dimensional quantum mechanics coupled to the bulk theory. In particular, the content of the 1D theory is a new one gauge field and charge 1 chiral multiplets and then charge -1 chirals. The charge is referred to this U1. And the coupling is realized by gauging the U1 flavor symmetry with the bulk vector. However, this is not enough because the infrared duality of ABJM is not simply mirror symmetry. There is also a T transformation which somehow mixes the electric and the magnetic part. So we conjecture that the latitude Wilson loop is dual to a mixed Wilson vortex loop. This is a conjecture, but we can try to realize this operator. And our proposal is to add a 1D level 1 Chern-Simons term for the U1 gauge field. In this way, we break the n equal 4 supersymmetry of the Asser-Gomis setup to n equal 2, but we still have conformal invariance, and this is broken by turning on a flavor gauge field for the U1 R-symmetry proportional to nu. As a consistency check, we have shown that as nu goes to 1, this mixed Wilson vortex loop is the only one reproducing the correct enhancement of supersymmetry. And we have also computed via localization the partition function of the mixed system, which amounts to compute this new refined with an index, and we have shown that it matches exactly the latitude Wilson loop. So in conclusion, we have developed a new localization scheme for the latitude supercharge. We have identified the dual operators for the bosonic Wilson loops in ABJM for k equals 1. And at the best of our knowledge, we have provided a way to define a novel type of mixed Wilson vortex loop. Thank you for your attention.
Thank you very much for the nice talk. Are there any questions?
May I ask a question?
Sure.
Sure.
So if I understand correctly, your problem with the cohomological localization is with the spin structure of the squash sphere, right?
My problem is that I don't have a ABJM is closed only on shell, and I have to do a supercharge.
Yeah.
So our proposal is that we can use this procedure explained by Cullen, because so he did for n equals 2, but all the relevant hypotheses are satisfied in our case, but there are some difference. The fact that the killing vector is not an n equal 2 killing vectors, it can be built only in an n equal 4 algebra, and also the fact that these are so it's a little bit involved to show that to find the precise mapping from ABJM multiplets to these cohomological multiplets. But we think that is not really an abstraction, but just a technical issue.
Okay, thank you.
Okay, good. Are there any other questions? So have you considered more general n equal 4 gauge theories?
Not yet, but a few days ago, there was a paper in where a similar Latitude Wilson loop was defined for Gaiotto-Witten theories with twisted hyper. And so I think that one of the future goals is to extend this kind of construction for those loop and see what happens.